Okay, good morning, everybody. Let's get started. As always, just a few housekeeping notes before we dive back into lecture material. First of all, I hope you're all doing well and coping with the current situation. Let's talk a little bit about the stream itself. Apparently, thanks to all of your attendance here on the stream, I've been upgraded to something called an affiliate on Twitch, which I still don't quite understand what that is, but apparently some of you may now see ads. So if you do see ads, let me know and I will try and extricate myself from being an affiliate. Hopefully there won't be too many distractions on the stream. Apparently if you follow or subscribe or something like that, you should no longer see ads if you are, but we'll see how things go. Let's talk a little bit about the final project. As promised at the beginning of lecture, I will mention a few things about sort of tips and tricks in PyroSim. I realize that there are quite a few differences now between the version of PyroSim, that you used, that you were directed to in Reddit, and the PyroSim that I mentioned last time, which is available at GitHub under mechlab/pyrosim. Some of you may want to switch over to this version. Unfortunately, that requires a reinstall, but of course you're not obligated to use any of the functions in here. There's still lots of interesting projects and ideas that you can carry out in the original version of PyroSim pointed to by Reddit. Any questions about final project? Just as a reminder to sign today's attendance sheet for the University of Vermont students. If there are not any questions, then we'll carry on. With lecture. And just as a reminder, we're working our way through some of the open problems in the field. Some of the open challenges, and we're looking at trying to scale evolutionary robotics up by inviting increasing numbers of non-experts to help us collectively train and evolve robots. And last time we ended by looking at the Twitch Plays Robotics project, which was an attempt to get non-experts to help robots ground language in action. And in the Dotbot project, which I introduced last time, the idea here is to see if we can invite non-experts to collectively design the bodies and then have an evolutionary algorithm evolve controllers for those bodies. What we were hoping for in both cases, or in the case of Twitch Plays Robotics, is to draw on the natural instinct of people to be good teachers, and we saw evidence of that in the fact that they issued short motoric language to the robots. In the Dotbot project, we're trying to draw on people's natural understanding of the relationship between body and motion, or biomechanics. Can people understand what makes a good body to simplify or facilitate an evolutionary algorithm training controllers for that body? So, I walked you through this cartoon last time, and I won't go through the details again, but just as a reminder, we have a bunch of people that are creating bodies, shown in gray here, and then their computer or other people's computer is running an evolutionary algorithm, and there's one evolutionary algorithm wrapped around each body. And what is the evolutionary algorithm doing? It is evolving an open loop control policy where it is rotating two connected cubes by a bar either in phase with one another, 0, 0, or 1, 1, or out of phase with one another, 0 and 1. So the zeros and ones represent the phase offsets, represented by the blue and red that you see in the panels down here. Okay, so we're going to see as we run this, when we ran this on the web, at the end, what is the fastest moving robot. We're going to compare that with a separate system in which people are still designing the bodies of robots, but in this case they cannot see and build upon each other's robot designs. So let me just skip ahead to the interface. When this website was up and running, This is what the user saw. I showed you a video of this last time. On the right, people are connecting the dots to build the robot body. And then once they have and they click go, there is a physics engine running in the browser that is it is evolving the controllers for that robot. In the first set of experiments, when a user arrives at the website, in the code we flip a coin, and if it's heads, we allow the user to see body plans made by other users, and it may be difficult to see in this screenshot here, but they can also see the fitness of the best controller evolved so far for those body plans. In the second experiment, when the user came to the website, when we flipped the coin, if the coin was tails, they were placed into a second group of participants where everything was the same except they did not see panel A. They were free to create any body plan they want and evolve controllers for it, but they could not see other people's designs. If two users in the second group happen to draw exactly the same body plan, then unbeknownst to those two users, they would share the evolutionary algorithm that is evolving controllers for that one body plan. Okay, so by creating these two groups of participants and by, in the first group, allowing them to collaborate and see each other's body plans, and in the second group, not, we can understand how much, what's the utility or the usefulness of people being able to collaborate and build on each other's ideas about what makes for a good body. So let's just walk through how this second group of participants operates. User one builds this body. They click go several times on their machine, which steps through an evolutionary algorithm evolving open loop controllers for this body. Same user then perhaps gives up on this body plan, makes a slightly different one, and continues and continues. In parallel to that, but unseen by user one, is user two, who is also making different body plans, and on and on and on. Okay, as I mentioned, the hypothesis here is that we want to see how well people do at creating body plans. We wanted to compare that against a third group, and this third group is made up of just machines, and in this case the evolutionary algorithm is going to be evolving populations of robots with differing bodies and differing controllers. So how well do humans do at building body plans compared to just machines or just evolutionary algorithms? Here are the results. So in red, we're seeing the third group, which is just an evolutionary algorithm, evolving bodies and brains. We're plotting on the horizontal axis here the number of evaluations, or the number of robots that are evaluated one after the other. And at the end of about 12,000 robots, the evolutionary algorithm has, the best robot is traveling about 15 units away from the origin. The green line corresponds to the second group. This is the independent group. All the humans are designing the body plans, but doing so independently. You can see that they did better than the red, but they did not do as well as the blue, which is the first team that I described to you, where humans are collaboratively creating body plans and evolutionary algorithms are evolving controllers for them. Blue did significantly better than green and red, so after a while we turned off the green team, meaning that if you came to the website, instead of flipping a coin, heads, you were placed in the first group where you could see each other's designs. Tails, you could not see each other's designs. We took away the coin and everyone was put into the first group where everyone could see each other's designs. And we continued to allow people to arrive at the website and contribute body plans and computational effort. I see there's a question here. Please go ahead and ask your question at any time. Can everybody hear me okay? Okay, Leonard, perhaps you have your computer audio turned off. Make sure you You are unmuted on Twitch. Okay, all right. Okay, so let's carry on. Sorry about that, everyone. Let's keep going. So we have this blue team again, which is the group of humans collaboratively building body plans together and evolving controllers for them. And you'll notice that after 11,000 robots have been collectively designed and evolved by the collaborative human team, they were doing significantly better than the machine team. So at least in this setting, what this means is that humans, or at least these humans, are able to intuitively build body plans that are easy to evolve controllers for, better than the evolutionary algorithms are at creating robot body plans for the evolutionary algorithm to evolve controllers for. So for most of you, hopefully that raises an interesting question, which is why? What is it about the bodies produced by the humans compared to the machines that are so good? Here's the sample of the 5 best bodies created by the collaborative machine team. So this is team number 1. Humans are collaborating to make bodies, and machines are collectively evolving controllers for them. Here are the 5 best body plans from the independent machine team. So humans are independently making robot body plans and not seeing each other's designs. Machines are evolving controllers for them. And then finally, here are the 5 best body plans from just the machine team. Clearly, the body plans produced by the machines are significantly different from those created by the humans. In what way? What are the features of this set of designs that distinguish them from this set of designs? If you have an idea, please go ahead and type it into chat. Exactly. One of the first features that should jump out to most of you is symmetry. Someone mentioned more connected. The human designs are a lot less complicated. So they are simple, depending on how we define simple, and also symmetric. When we gave the instructions, to the human participants, we did not tell them to make symmetric designs. They spontaneously did that. Presumably because most of us realize, consciously or unconsciously, that if you need to move as quickly as possible away from a point, which in this case is the origin, the best way to do so is with a symmetric body plan. So that's the first feature that jumps out. Again, as somebody mentioned, a lot less complicated. It turns out that there are other features of these bodies that distinguish them from the machine team. And we will look at those features in a moment. But what we want to try and do in this next phase of the experiment, now that we know that humans are better at making bodies, robot bodies, than machines, can we extract from the crowd those features like symmetry and simplicity? Can we automatically distill out those features? Or can we use those features to improve the automated design of machines? Now, why would we want to do that? If humans are so good at this, why don't we let humans do what they're good at and let machines do what they're good at? One of the reasons we might want to automate this is, again, remember that our goal is to try and scale things up. We're dealing with a very simple simulator and a very simple environment. We'd like to create much more complex machines with many more motors so they're able to move over rugged terrain, crawl through apertures in a pile of debris, and so on. It probably won't make sense to scale this up if we repeatedly ask humans to keep designing bodies for new robots and new environments. So in this first phase of the experiment, you can think of this as crowdsourcing. In the second phase of the experiment, we're going to extract these features and bias the evolutionary algorithm to include those human features into the machine designed features. So this second experiment you can think of as crowd seeding. And in crowd seeding, as the name implies, we're going to try and seed or bias evolutionary search towards these features like symmetry and simplicity. So how are we going to do that? Well, we're going to use multi-objective optimization like we've seen before. And just as a reminder, in multi-objective optimization, we're going to have multiple objectives. And the first objective is going to be d, distance away from the origin, as we usually did. And in the first phase of this experiment, that was all we were evolving for, distance away from the origin. On the second objective that we're now going to introduce, the second objective is going to be features that describe the robot itself. So we're going to take symmetry and we're going to take symmetry on the second axis and divide it by 1 plus C, which is the number of connected components. So what is number of connected components? Well, you'll notice if I go back to some of the human and computer designs, you'll notice that you could actually connect the dots and make multiple pieces. You don't see those multiple pieces here in the machine team, but in fact in the machine team there are a lot of designs in which they actually made multiple robots or multiple disconnected components. So we're going to compute C here. We're going to compute C by counting up the number of connected components in any one robot design. And this additional value S, we're going to compute as symmetry. This is a value that's going to range between 0 and 1. How do we define symmetry? Well, we're going to take any one design and cut it using various planes and ask whether objects on one side of the plane are matched to objects on the other side of the plane. So if we cut this trident design here down the vertical axis, then it is symmetric. If we cut it along the horizontal axis and flip it over, it is not symmetric. So we're going to be placing a large number of these symmetric lines and then flipping the design over either side. And if the two sides match, we get a high value of S for that symmetric cut. And we're going to do that cut many times for each design, and the maximum value of S for any one of those cuts is going to be the value of S for that design. Make sense? Any questions? Okay, so remember now we have two objectives, distance and S over 1 plus C. You should be able to convince yourself by looking at this equation here that we're going to try and maximize S, symmetry, and minimize C. We want to have one connected component. So what that does is give us, for a population of robot designs, each design represents a point in this two-dimensional plane. And in multi-objective optimization, we are trying to push up and to the right.